My name is Arjun. I've been working with LinkedIn since 2014 as a part of the data SRE team. So basically, we manage all the storage layer applications at LinkedIn. So let's start off with a question. Show of hands, how many of you are regular users of LinkedIn? Okay, that's pretty good. So when you're using LinkedIn, you might have noticed that you interact with a lot of images or PDFs and stuff. Basically, whether it be reading through someone's profile or reading a post or sending an attachment through the email. So you interact with media a lot. Now let's take another example. Let's take Amazon. Can you imagine how hard it will be to do online shopping if you can't see the image of the thing that you're buying? It'll be really hard, right? So what I'm trying to say is that media these days plays a very significant role in any organization. So different companies have different ways, different approaches of how they handle media, how they store media, how they process it, stuff. At LinkedIn, we use Ambry for storing all these media files, basically these profile pictures, logos, PDFs, and all sorts of static files. So Ambry is basically an immutable blob storage system. For those who don't know, immutable means you can't update. Basically, you can do a put, you can do a get, and you can delete. But there's no concept of modifying whatever you have put. If you want to put if you want to change the image, you have to put it again. Now, before we get into Ambry and what it can do, I'd like to talk to you about what made us decide that we needed something new, basically our motivation. So back in 2012 or early 2012 or 2011, we were using some sort of legacy system known as media server. So this is kind of how it looks like. So basically, we used a bunch of filers to store the objects. And in these filers, each object was stored as a separate file. And these objects were NFS mounted. And there was a separate database for storing the metadata, like the location of the file and other system data. So this setup had a lot of issues. Basically, first of all, these filers were a black box. We had a limited set of metrics to look into, and all that resulted in us having a very hard time to troubleshoot. So high MTTR. Whenever an issue happened, it took us a long time to find out what's wrong. Another thing is that there was a lot of back and forth between the metadata DB and the filer. So even for one single lookup, there was a lot of about 3 to 4 disk reads. So operational overhead. Now, this operational overhead, combined with the fact that it was NFS mounted, we came to the conclusion that it was not going to scale to the high network that we were expecting. And the last issue that the most common one was that these filers were really hard to maintain, as in really expensive. So it wasn't a very cost-effective solution. So at that point in 2012, we decided we needed a new solution. And we decided that the new solution that we were going to go with should have these qualities. So it should be a reliable system. It shouldn't go into failures more often or anything. It should be something that should be very easily scalable. We shouldn't have to worry about scaling it. It should be easily done. Something with a very low MTTR. Basically, if we ever come into an issue, we should be able to fix it then and there itself and then go back with our lives. Then we were going for an active-active setup because we had multiple data centers. And we wanted all the instances of our storage to be equally capable of handling both reads and writes. And last but not the least, something which would be cost-effective. So now that we knew what we wanted, we decided to do a little digging around. We wanted to see in the market what's available. So we considered a lot of solutions, and some of the most amazing ones that we came across were object store systems like React.cs. We also saw other filer-based systems like EMC's Isilon. We considered clustered file systems like Mapper. So all these solutions were pretty good. They solved almost all our requirements, but there were some things that weren't going well with us. Like some of them didn't have an active-active setup per se, and implementing that would have been a little much of an effort. And some of them even promised other features which we didn't want, something like extra security, because we really didn't want our applications to be bothered with security, because we had other applications in our stack which already took care of these security matters. We didn't want the storage layer to be burdened with that overhead. So again, as a side note, guys, this was done back in early 2012. I'm pretty sure that most of these systems have already gone past these hurdles. I know for a fact that they are providing most of the features that we are also providing right now. So now, maybe some of you might be thinking, did you consider S3? But yeah, we did consider S3. S3, in fact, came closest to our needs. With S3, we wouldn't have to worry about scaling the solution. We didn't have to worry about capacity planning or any of those things. But the thing is, if we were to go with S3, the applications that directly dependent on our database, they would have had to use the S3 API to get the data. And that would mean a lot of requests going outside our data center onto the cloud. So, and that would introduce a lot of latency. Now, you can say that you can migrate those applications as well onto the cloud, but that would have been a huge coordination of moving a large part of our stack onto the cloud as well. And we weren't comfortable with some parts of our applications being outside our data centers. So at that point, we kind of decided that we needed our own solution. So from our research, we decided that we were going to go ahead with a blob storage solution. So, and we took some of the ideas from the existing white papers. So the two main papers that gave us the idea of a blob storage and how to approach a blob storage were Facebook's Haystack and Twitter's Blob Store. So if you know these papers, you might be very familiar with what I'm going to tell you further. So coming on to Ambry. So like I said, first of all, it's an immutable blob storage system. So there is no concept of updates. You can just do a put, get, and a delete. Next, it's a handle-based solution. So when you do a put, you get a ID or a handle, and all further processing is done by passing that handle onto the system. It's a horizontally scalable system. Basically, you can just add more hosts to scale the system. It scales in the petabyte range, and it supports custom metadata. So two things is that one thing is the user can also add whichever metadata that he or she wants along with the blob that they are uploading. And the metadata is stored alongside the blob. There isn't a separate storage requirement for the metadata. It's an active-active setup like we were going for. So all instances can handle both reads and writes equally well. And the latest feature that we support is large blob support. So we now currently support writes from as small as a few kilobytes to multiple gigabytes. Let's take a look at the architecture. So the architecture is pretty simple. It has just three main components. You don't have to get intimidated by what I've put here. So there are just three main components: the front end, the Ambry server, and the cluster map. These three interact with each other, and that's pretty much what Ambry does. And so most of the customer requests are handled by the CDN. Now, in case there's a miss in the CDN either queries the internal clients or queries Ambry directly. So most of all the client requests go to the front end, The front end acts as a bridge between the clients and the server nodes. It uses the data in the cluster map manager to route the request to the appropriate server nodes and returns the data. Now let's take a look at the components one by one. Front end. So as I said before, the front end, the first responsibility is that of coordination. It takes a request from the clients, routes it to the appropriate server nodes, and returns the response. The front end also does security. Basically, it interacts with other applications in the LinkedIn stack, such as antivirus and authorization services, to ensure that the blob that we are receiving is a safe blob, and whoever is querying for the blob has the authority to do so. Now, with respect to the front end, we recently released something known as the non-blocking front end. It follows the non-blocking paradigm or the asynchronous paradigm, which results in efficient thread utilization. It promises a lot of features like chunking and streaming gets and streaming puts. So I'm not going to go into the details right now. You can ask me even later on. Now the server, the first responsibility is that of storage. The server also communicates with each server nodes, communicate with the other server nodes to keep each other in sync, like replication. And one thing about the server node is that we use JBOD hosts rather than the standard RAID hosts. Now coming to the third component, the cluster map. The cluster map is a set of static files that we use to maintain the state, know and maintain the state of the cluster. The first static file is the hardware layout file. This file contains details about the state of the node, whether each node is available or whether a given node is down for maintenance and stuff. It also contains the state of the disks and the metrics like disk capacity. The second layout file is known as the partition layout file. So partition here is a logical partition that we use. We separate the logical layer from that of the physical mapping, and this layout file is the one that maintains that mapping. So you can see that for each partition there will be a set of nodes which will contain the replica of the partitions. And the other feature with the partition layout that we use is that of the partition state. So you can see a metric called the partition state. It can have two values, either read write or read only. So in case the partition goes above 80% of capacity, you can change it to read only so that that partition won't accept further writes. Now let's take a look at how they interact with each other for the different queries that come along. So for a simple put workflow, the client sends a request to the front end. The front end chooses one partition based on the data in the cluster map. It generates a blob ID based on the partition number. So the blob ID is an alphanumeric key. I'll show you a sample blob ID later on. It's an alphanumeric key which has the partition number and a unique random number for each blob. Once a blob ID is generated, the data is sent to the appropriate server nodes which contain the replicas. Now here, as a standard, now we set 3 replicas per data center, which is again configurable. You can add more replicas if needed. And it waits for, once the put signal has been given out, it waits for 2 acknowledgements. Again, the number 2 can be configured. It's a trade-off between latency and consistency. And once it gets 2 acknowledgements, it returns the blob ID to the client. Now you may wonder about the third write that is sent. Now in case that if the third write fails, replication will take over and you will get the blob replicated onto the third node straight away. We don't have to worry about it. And as I said, the blob ID is an alphanumeric value. It looks something like this. Now, mentioning some numbers for put blob, the average QPS that you get is around 300 to 500 every day. It varies a lot depending on the situation. The latencies for a small blob, that is usually less than 100 kilobytes, it's less than 10 milliseconds. For a slightly bigger blob, within the range of 100 KB to 4 MBs, it goes from 10 to 20 milliseconds. Now, for an extremely large blob that's beyond 4 MB or in multiple GBs, it can go to 50 or more, depending on the size. Now, coming to the GET workflow, the client issues a GET along with the blob ID. The front end determines the partition based on what is in the blob ID. It routes the request to the appropriate server nodes, waits for one acknowledgement, and passes the blob back to the client. Now, in certain cases, if you have multiple data centers, like you have one in Texas and one in Singapore. So, if you put a blob in Singapore and someone immediately or almost immediately within a set of nanoseconds requests the same blob back in Texas, there might be a blob missing scenario, right? So, that's an availability issue. So, what we do to take care of that is that the front end can query the server nodes in the other data centers directly as well. So, as I was saying, basically if the GET request comes from the client to the front end and it's a 404 here, it goes cross colo to the other data center, waits for the response and sends it back to the client. Some numbers again, basically the average QPS is around 24K. Latencies for a small blob, it's less than 15 milliseconds. For a slightly bigger blob, it can go from 75 to 100 or above in extreme cases. For a large blob, it's usually less than 200 milliseconds, but it can go higher depending on the size of the blob. Now, the third interaction is that of replication. So, like I said before, replication is a process by which two server nodes communicate with each other and to keep each other in sync. So, this happens in two round trips. So, in the first round trip, the first node queries the second to get the blobs that were recently put, or get the blobs that were put in the second blob, the second server node, since a given time period. The replication thread of the second node queries the local store for getting a list of the blobs that were recently put. The store responds with the list of blobs or blob IDs, not a blobs, my mistake. That list of blob IDs is given back to the first server node, which checks in the local store if the same blob IDs are already present. Now, in case it finds certain nodes, certain blobs that are not present in this, that are there in this list, it queries the second node for those specific blobs. That is fetched from the local store of the second blob, second server node, and returned to the first. So, the replication time between data centers goes from 20 to 100 milliseconds. Again, guys, this is not very accurate because it can change depending on how far the data centers are and the blob size as well. Just keep in mind that it's two round trips. The replication time inside a data center is usually less than 10 milliseconds. Again, it depends on the size of the blob, if at all the whole blob is being replicated inside the data center. So, mentioning some numbers overall, we currently have a capacity of 900 terabytes, of which we are serving 300 terabytes of capacity, and we are growing at a rate of 1,100 GB per day. This again fluctuates. We take weekly measurements. And as I said before, we are using Ambry in LinkedIn for images, PDFs, videos, and all sorts of static files. We've recently open sourced this back in 2016, and we've also written a blog post about it. So you can go ahead and read up if you want more details. And all sorts of contributions are welcome as well. Thank you. Any questions? You guys can use the mic.
So going back to the last slide, so after the 900 terabyte limit, what do you do? You discard the.
We don't discard. No, we.
So you fill up like 1.1 terabyte per day. So.
Yeah. So we get more hardware and scale it up.
So so your current capacity is 900 terabyte.
Current total data is 900 terabytes.
Oh, okay. So it's not. It's the total data. It's not your capacity.
Yeah, we'll expand it further if the need arises like that.
Okay. All right. So I have another question. It's going back to your to the point where the front end is trying to send data to all multiple data centers located geographically in different locations. Oh, and you said that could be like a millisecond latency, where if you go back a few slides.
Is it the get or the? Is it with respect to gets or?
Just the one before this, the slide before this. Yeah, here. So you said you could get a 404 if.
So yeah, this is happening only if someone is the client is doing a get in the first data center before replication has already had the time to transmit the blob.
Yeah, I understand. This is not related to my first question. This is different. Okay. So you try to write to all three data nodes. Data has been written to only one, but you're trying to get from the other node within a very short interval of time. That's when this is happening, right?
See, suppose there was a write in the second data center, and almost immediately someone in the first data center.
Yes. So why not have like a caching layer in between, which handles this, which says, hey, okay, now I acknowledge that all the data nodes have been written with this data, and then serve from the cache until it's been. Why keep rerouting to different data nodes?
So this is to address the corner case, like I said, almost immediately in a matter of nanoseconds if the query happens. So even if there is a caching layer, do you think that it will have the same amount of time to? It will be the same thing in the caching layer as well, right? In the data center, in the second data center, the caching layer might pick it up, but the caching layer in the first data center should also be.
So it's not between the different data nodes within a data center. You're talking about.
Yeah, this is between data centers.
Got it. All right. Thank you.
Okay. Any other questions? Cool. Thanks, guys. I'll be around if you need me.